Could our universe, with its billions of galaxies, exist inside a black hole? This question, once purely theoretical, now drives cutting-edge research in astrophysics. To explore this idea, we need to understand what a black hole is and how our universe might mirror its structure. Let's break it down clearly and systematically. A black hole is a region where gravity is so strong that nothing escapes, not even light. It forms when a massive object, like a dying star, collapses into an incredibly dense point. This point, called the singularity, warps spacetime, the four-dimensional grid that defines how objects move and time flows. Picture spacetime as a network of coordinates, not a physical surface, twisted tightly around the singularity by its immense mass. The boundary of a black hole is known as the event horizon. This invisible sphere marks the point where gravity becomes absolute. Anything crossing it, from a starship to a beam of light, is drawn inward with no chance of return. The event horizon's size depends on the black hole's mass. For example, a black hole with 10 times the mass of another has an event horizon 10 times larger, as calculated by the Schwarzschild radius formula. Now let's look at our universe. It has its own boundary, called the cosmic horizon. This is the farthest distance from which light can reach us, given the universe's age of about 13.8 billion years. Light travels at 299,792,500 a second. Beyond the cosmic horizon, roughly 46.5 billion light-years away, light hasn't had time to arrive due to the universe's expansion. Here's the key connection. The observable universe contains an estimated 1.5×10^53 kg mass, including stars, planets, gas, and dark matter. If this mass were compressed into a black hole, its event horizon would span about 46.5 billion light-years, nearly matching the cosmic horizon's size. The universe's average density, approximately 1 to 10^7 kilojoules per cubic meter, also aligns with the density of a black hole of that scale. The match is not trivial. It suggests our universe's structure resembles a black hole's. The question is whether this is a coincidence or a clue to our origins. To investigate, we must delve deeper into black hole physics and examine evidence from our cosmos. This hypothesis, grounded in observation and mathematics, sets the stage for a profound scientific inquiry. The idea that our universe might exist inside a black hole hinges on advanced physics. Albert Einstein's theory of general relativity describes how mass and energy shape space-time inside a black hole. This shaping becomes extreme past the event horizon. Space-time curves so tightly that it forms a new region, separate from the outside universe. This region acts like a distinct cosmos, with its own rules and structure. If our universe is inside a black hole, we could be living in this isolated space-time. The event horizon would shield us from the external universe, making it impossible to see beyond. Our observable universe, defined by the cosmic horizon, might be the interior of this black hole. This model suggests our reality emerged from a black hole's core, a concept supported by mathematical solutions in general relativity. To understand this, consider how gravity works. It treats gravity not as a force, but as a curvature of space-time. Massive objects like stars bend this grid, causing nearby objects to follow curved paths. In a black hole, the curvature is so intense that all paths lead to the singularity, a point of infinite density beyond the event horizon. However, equations predict a new space-time, potentially vast enough to house a universe like ours. Recent research offers clues to test this hypothesis. Astronomers have studied the rotation of spiral galaxies, which resemble spinning pinwheels of stars. A study examined several hundred galaxies using telescopes to observe their motion. The findings were unexpected. About 2 out of every 3 galaxies rotated in a direction opposite to our Milky Way galaxy. This pattern was seen in observations above and below the Milky Way's plane. This rotational bias is significant. In a typical universe, galaxy spins should be random, with half rotating one way and half the other. A 2-3 preference suggests a coordinated motion across vast distances. This could indicate that the entire universe has a net rotation, a property described as angular momentum. Angular momentum measures how much an object spins and in what direction. Why do galaxies spin at all? When galaxies form, they start as clouds of gas and dust. As these clouds collapse under gravity, any small motion within them grows stronger. This is due to a law called conservation of angular momentum. A large, slowly moving cloud becomes a smaller, faster spinning galaxy. This explains why individual galaxies rotate, but a universe-wide rotational pattern is harder to explain. If the universe has a net rotation, it challenges standard models. The Big Bang theory assumes the universe expanded evenly in all directions with no preferred spin. A rotating universe suggests a different origin, possibly tied to a black hole. This connection is intriguing, but requires more evidence to confirm. The discovery of a possible universe-wide rotation raises deep questions. In most cosmic models, the spins of galaxies should be random. Each galaxy forms from a collapsing gas cloud with its own unique motion. These motions, driven by turbulence, typically cancel out across the universe. A net rotation, where galaxies prefer one spin direction, suggests an unexpected order. This finding challenges our understanding of the universe's origin. Angular momentum is the key concept here. It describes how much an object rotates and in what direction. For example, a spinning top has angular momentum, which keeps it upright. In the universe, every rotating object from planets to galaxies carries angular momentum. This property arises during formation. As a gas cloud shrinks, its rotation speeds up, much like a dancer pulling in their arms to spin faster. This is called conservation of angular momentum. In a typical universe, the angular momentum of galaxies should balance out. Half should spin one way, half the other, with no overall preference. The recent study of several hundred spiral galaxies found otherwise. About 2 out of every 3 galaxies rotated opposite to the Milky Way galaxy. This bias, observed across vast distances, hints at a universe with net angular momentum,
reflecting the deep interconnectedness of space and time.
Special relativity describes a universe without gravity, where space-time is flat and unchanging. But Einstein knew this was only part of the story. His next leap came with the general theory of relativity, published in.
Here, he introduced the idea that space-time is not static but can curve and warp under the influence of mass and energy. Think of space-time as a rubber sheet. When you place a heavy object like a bowling ball on the sheet, it creates a dent. Smaller objects rolling nearby will follow curved paths, not because of a mysterious force pulling them, but because the sheet itself is distorted.
Similarly, massive objects like stars and planets bend the fabric of space-time, guiding the paths of nearby objects. This is the essence of gravity in Einstein's framework, not a force, but the geometry of space-time itself. The implications of curved space-time are profound. Light, which always travels in straight lines in flat space-time, follows curved paths near massive objects, leading to phenomena like gravitational lensing, where the light from distant stars and galaxies is bent around intervening masses, creating stunning arcs and rings in the sky. Einstein's equations also revealed that time flows more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. This effect has been experimentally verified by placing precise atomic clocks at different altitudes. Clocks closer to Earth's surface, where gravity is stronger, tick more slowly compared to those at higher altitudes for everyday life. This difference is minuscule, but it becomes critical in technologies like GPS, where accounting for time dilation ensures the system's accuracy. Nowhere is the unification of space and time more dramatic than near black holes. These enigmatic objects warp space-time so severely that not even light can escape their grasp. The event horizon, a black hole's boundary, represents a point of no return where space-time curvature becomes infinite. Beyond this horizon, time and space as we understand them cease to exist. For an external observer, an astronaut falling toward a black hole appears to slow down, their time stretching infinitely as they approach the event horizon. To the astronaut, however, time continues normally as they plunge into the unknown. This bizarre behavior arises from the extreme warping of space-time, a direct consequence of Einstein's equations. Space-time is not merely a backdrop, but an active participant in the dynamics of the universe. It governs the motion of planets, the behavior of light, and the evolution of galaxies. The ripples in space-time, known as gravitational waves, were first predicted by Einstein and later detected by the LIGO experiment in 2015. These waves, generated by colossal events like black hole mergers, carry information about their origins, opening a new window into the universe. Einstein's unification of space and time marked a profound philosophical shift. It challenged our intuitive notions of reality, replacing them with a vision where the universe is a dynamic, interconnected whole. Time is no longer an absolute tick of a cosmic clock, and space is not a static grid. Instead, they form a fluid tapestry shaped by mass, energy, and motion. This new understanding extends to the very fabric of existence. The holographic principle, inspired by black hole physics, suggests that space-time itself may be an emergent phenomenon arising from deeper quantum mechanical principles. Such ideas push the boundaries of modern physics, hinting at a reality even stranger than Einstein. Gravity's curved fabric. Imagined in 1916, just a year after Albert Einstein introduced his general theory of relativity, Carl Schwarzschild provided the first exact solution to Einstein's equations. This groundbreaking work described the geometry of space-time around a spherical, non-rotating star. Schwarzschild's solution went on to reveal some of the most fascinating phenomena in physics, including the concept of black holes, although the term itself was not introduced until decades later.
At its core, Einstein's general relativity reshaped our understanding of gravity. It described gravity not as a force, as Isaac Newton had proposed, but as a curvature in the fabric of space-time caused by the presence of mass and energy. To understand this, imagine space-time as a flexible sheet. When you place a heavy object like a bowling ball on the sheet, it causes the surface to bend. Smaller objects placed nearby naturally roll toward the heavy one, not because the larger object is pulling them, but because they are following the curve of the sheet.
Schwarzschild's solution mathematically formalized this bending. He showed that space-time around a massive object is not flat, but curved. The degree of curvature depends on the object's mass. For smaller objects like the Earth, this curvature is gentle, but for extremely massive objects like black holes, the curvature becomes so extreme that it creates a boundary from which not even light can escape. In general relativity, the curvature of space-time is described using a mathematical framework called the metric. The metric is essentially a tool that relates the coordinates of space-time to the actual distances and times experienced by objects within it. In flat space, such as a tabletop, the metric is simple. It reflects the familiar Pythagoras' theorem, where the distance between 2 points is calculated based on their positions. In curved space-time, the metric becomes more complex because it must account for the bending of space and the dilation of time caused by gravity. Schwarzschild's metric was the first to describe how this works near a spherical mass. It provided a way to calculate how distances and times are stretched or compressed due to the presence of a massive object. To visualize space-time curvature, think about the surface of the Earth. Although the Earth is round, Small areas like a football field appear flat to us. Mathematically, you can describe distances on these small patches using flat geometry. But as you consider larger areas, the curvature of the Earth becomes apparent. The same principle applies to space-time. While space-time may appear flat in small regions, its curvature is evident over larger scales or near massive objects like stars and black holes. Schwarzschild's metric takes this idea further. It reveals that space-time is stretched, not only in space, but also in time. Near a massive object, time itself slows down relative to regions farther away. This phenomenon is called gravitational time dilation. For instance, a clock positioned near the surface of a massive star ticks more slowly than a clock far from it.
Schwarzschild's solution introduced a critical concept, the Schwarzschild radius. This radius defines the size of a region around a massive object where the curvature of space-time becomes so extreme that nothing, not even light, can escape. This boundary is known as the event horizon. For an object like the Sun, if it were compressed into a sphere with a radius of about 3 kilometers, it would become a black hole with its event horizon defined by the Schwarzschild radius.
The event horizon is not a physical surface, but a point of no return. Anything crossing this boundary is irrevocably drawn toward the singularity, a point where space-time curvature becomes infinite. Inside this region, our understanding of physics breaks down. Schwarzschild's solution initially described the space-time around stars, but it also laid the groundwork for understanding black holes. By stripping away the matter within the Schwarzschild radius, what remains is a pure black hole, a region of space-time defined entirely by its geometry.
The curvature in this region is so severe that it creates a singularity at the center, where the density of matter and the strength of gravity become infinite. Time and space are profoundly affected near a black hole. An outside observer watching an object fall toward the event horizon would see the object slow down as it approaches the boundary. Time for the object appears to freeze as it reaches the event horizon. For the object itself, time continues as normal, and it crosses the horizon without noticing any dramatic change.
The warping of space-time has observable consequences. One of these is gravitational lensing, where light passing near a massive object is bent, creating distorted or duplicated images of distant stars or galaxies. This effect is commonly observed around massive galaxy clusters and provides valuable insights into the distribution of matter, including dark matter, in the universe.
Another effect is the slowing of time near massive objects, as seen in experiments with GPS satellites orbiting Earth. These satellites experience slightly weaker gravity than we do on the ground, so their onboard clocks tick faster. Engineers must account for this time dilation to ensure accurate navigation data. While Schwarzschild's metric describes the space-time around a spherical mass, it is essential to distinguish between local and global effects. Locally, space-time may appear flat, and objects follow straight-line paths called geodesics. Globally, these geodesics reveal the curvature of space-time, bending toward massive objects. This distinction helps explain why astronauts aboard the International Space Station feel weightless. They are in free fall, following a geodesic through the curved space-time created by Earth. Though they experience no force, their path is continuously bent toward the planet, keeping them in orbit.
Einstein's general relativity is remarkable because it applies universally, from small-scale interactions near planets to the vast cosmic distances between galaxies. Schwarzschild's solution is just one of many metrics that describe specific scenarios, but it set the stage for understanding more complex phenomena, including rotating black holes, known as Kerr black holes, and charged black holes, known as Reissner-Nordström black holes.
General relativity also predicts phenomena like gravitational waves, ripples in space-time caused by accelerating masses. These waves were first directly observed in 2015 by the LIGO experiment, confirming yet another of Einstein's predictions.
One of the most counterintuitive aspects of general relativity is the interplay between time and space near a black hole. Both are stretched to their limits. For someone falling into a black hole, time appears normal from their perspective, but to a distant observer, their motion slows to a standstill. This apparent contradiction arises because time and space are not fixed, but are part of the same dynamic fabric influenced by gravity. The concept of geodesics helps clarify this. Objects move along the shortest paths in space-time.
We are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here in this realm of the unknown that we may find the answers to the questions that have haunted humanity for centuries. As we venture deeper into the mysteries of black holes, we find ourselves drawn into a world of wonder and awe. A world where the laws of physics are but a distant memory, where the rules that govern our universe are but a faint whisper in the wind. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. As we continue to explore the mysteries of black holes, we are reminded of the profound impact that these entities have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. As we venture deeper into the mysteries of black holes, we find ourselves drawn into a world of wonder and awe, a world where the laws of physics are but a distant memory, where the rules that govern our universe are but a faint whisper in the wind. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. As we continue to explore the mysteries of black holes, we are reminded of the profound impact that these entities have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. As we venture deeper into the mysteries of black holes, we find ourselves drawn into a world of wonder and awe, a world where the laws of physics are but a distant memory, where the rules that govern our universe are but a faint whisper in the wind. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. As we continue to explore the mysteries of black holes, we are reminded of the profound impact that these entities have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. As we venture deeper into the mysteries of black holes, we find ourselves drawn into a world of wonder and awe, a world where the laws of physics are but a distant memory, where the rules that govern our universe are but a faint whisper in the wind. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped.
It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries.
As we continue to explore the mysteries of black holes, we are reminded of the profound impact that these entities have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe. For in the heart of these cosmic gatekeepers lies a realm where the laws of physics are rewritten, where the very fabric of space and time is reshaped. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. As we venture deeper into the mysteries of black holes, we find ourselves drawn into a world of wonder and awe, a world where the laws of physics are but a distant memory, where the rules that govern our universe are but a faint whisper in the wind. It is here, in this realm of the unknown, that we may find the answers to the questions that have haunted humanity for centuries. And so, as we stand at the threshold of this new understanding, we are reminded of the profound impact that black holes have on the very fabric of our universe.
To understand what a naked singularity truly is, we need to revisit the heart of general relativity
When massive objects collapse under their own gravity, relativity tells us they can form black holes, regions where space and time bend so severely that not even light can escape. At the core of this black hole lies the singularity, the endpoint of gravitational collapse. But what protects us from the singularity is the event horizon. It's like a cosmic cloak, ensuring that all the dangerous physics, those infinite curvatures and unresolvable equations, remain hidden from the universe.
In 1969, Roger Penrose, one of the architects of modern relativity, proposed that this cloaking isn't accidental. It's a principle. His cosmic censorship conjecture suggests that nature abhors naked singularities, always ensuring that singularities come dressed in horizons. This conjecture implies that we are spared from directly witnessing the most extreme expressions of space-time gone rogue. The universe enforces a kind of censorship not to deceive but to preserve the integrity of physical laws as we know them.
However, physics isn't governed by ideals. It's driven by equations. While general relativity models black holes beautifully, it can also generate scenarios where collapse doesn't result in a cloaked singularity. These solutions are rare, often relying on exotic configurations, imploding dust clouds, finely tuned angular momentum, or specific forms of matter. But they do exist. They linger on the edge of possibility in simulations and theoretical constructs, stretching the boundaries of known stability.
In recent years, these possibilities have become harder to ignore. In 2023 and 2024, advanced numerical simulations powered by modern supercomputers and improved methods for solving Einstein's equations began to reveal something astonishing. Under certain precise initial conditions, it appears that gravitational collapse can lead to a singularity without forming an event horizon. These simulations don't rely on exotic matter or fantastical physics. They simply allow the equations to unfold, producing results that challenge the very foundation of cosmic censorship.
These aren't just theoretical what-ifs anymore. They are mathematical blueprints, hinting that the universe may, under specific circumstances, allow its core to be exposed. But what does this exposure mean? A naked singularity is not just a glitch. It's a fundamental violation of causality and predictability. In a black hole, we lose information behind the event horizon, but we understand the structure of that loss. We can model the black hole's exterior, track Hawking radiation, and theorize about its eventual evaporation.
But a naked singularity offers no such comfort. If it is visible to the outside universe, if light and particles can interact with it directly, then the laws of physics break down in public. Predictive power disappears. The future evolution of the universe becomes ambiguous because the singularity can influence distant regions in ways that no known rule can constrain. This kind of unpredictability isn't just a theoretical nuisance, it's a crisis for determinism in physics.
Determinism means that, given a set of initial conditions, the future is calculable. But if naked singularities can influence events beyond their core without the mediation of an event horizon, then all bets are off. They become the ultimate wild card, the cosmic equivalent of tearing a hole in a well-written script and letting chaos improvise.
Despite their potential to disrupt, naked singularities are captivating. If they exist, they offer a direct window into the unknown. Unlike black holes, which hide their singularities forever, naked singularities are exposed. They emit signals, they interact with particles, they offer data. In theory, one could study the raw gravitational field around such a singularity, measure the behavior of light curving through it, and observe the ultimate manifestation of warped spacetime. But would that singularity be aware of us? No, not in any conscious sense. A naked singularity, however dramatic, is still a construct of physical law. It doesn't think, it doesn't feel, It doesn't choose, it merely exists suspended in a gravitational screen, deforming everything around it. Unlike consciousness, which emerges from layers of complexity, interdependent networks, and feedback loops, a singularity is pure distortion. It is what happens when space and time are stripped down to their mathematical bones. Yet the idea that such an object could interact with the universe without cognition or awareness presents a unique philosophical dilemma. In physics, observation implies a transfer of information. But what happens when the observer isn't sentient? When the thing receiving the information is not a mind, but a tear in the fabric of causality?
This is the realm of raw interaction. A naked singularity could, in theory, absorb and emit particles. It could bend light, twist space, and accelerate objects. But it would do so without filters, without purpose. It would be the universe experiencing itself without interpretation.
The closest analogy would be a camera that records, but never plays back, never edits, never understands. A mechanism that captures inputs, but assigns them no meaning. And still that kind of interaction, meaningless though it may be, matters. Because physics at its core is built on the relationships between things. Mass affects mass. Energy curves space-time. Fields fluctuate and collide. Whether or not a singularity is conscious is irrelevant to its influence. Its gravitational field speaks volumes. Even if it understands none of what it says, there is something unsettling about this idea that a naked singularity could bend, transform, and watch us, and yet know nothing. It's the coldest kind of attention, mechanical, blind, and absolute. It doesn't judge. It doesn't forget. It simply warps. This concept brings to mind the ancient philosophical notion of the unmoved mover, something that affects everything while remaining untouched. But where Aristotle imagined a divine intelligence, the naked singularity is its opposite. It is not divinity, but discontinuity. Not a source of order, but a rupture in it. As of now, we have not observed the naked singularity. We've only theorized. The real universe may still enforce cosmic modesty, cloaking her extremes behind event horizons. But the more we simulate and explore, the harder that assumption becomes to defend. The mathematics seems to be on the side of exposure. And if that's true, we may one day detect signs, not just of black holes, but of something deeper, something unresolved. Strange flares, unexplained gravitational lensing, time distortions with no horizon to anchor them, clues that something truly bare lies at the edge of visibility. Not all physicists agree on the interpretation of these simulations. Some argue that naked singularity solutions are mathematical curiosities, unstable under the slightest perturbation, unlikely to arise in the messy real-world collapse. A universe with dust collapsing in perfect spheres is not the one we see outside our windows. But that critique, while valid, doesn't rule out the possibility. It only underscores how delicately balanced the laws of nature might be, teetering on the edge between exposure and concealment. What if exposure is not a flaw, but a feature? What if naked singularities are nature's way of revealing that even her most forbidden truths are accessible, eventually? That behind every horizon lies the potential for revelation. If so, the naked singularity is not the villain of physics, but its muse, the ultimate challenge, calling us to rethink causality, to reconstruct our tools, to transcend the safety of cloaks and curtains.
One might even argue that the singularity is not what's naked we are. Stripped of certainty, stripped of laws that always work, stripped of the comfort that there's always an equation to rely on, the moment we confront a naked singularity is the moment we confront our limits,
It's the universe in full, unapologetic clarity saying, "Here is what I am," with no veil.
Yet it remains a question whether such honesty can ever be fully witnessed. If such objects exist, they may be fleeting, unstable, ephemeral. They might dissolve back into cloaked black holes, or they may signal conditions too extreme to persist.
Perhaps they require universes with different constants or geometries. Or maybe we already live in such a universe and we simply haven't looked hard enough or in the right direction.
Either way, the naked singularity represents a unique threshold, not of knowledge per se, but of exposure. It doesn't just sit at the end of a collapse. It sits at the beginning of a new kind of physics, one where old boundaries no longer hold, and the raw, unresolved truth of the universe stands without disguise.
In that truth, there is neither consciousness nor intent. Just interaction, just distortion, just the raw, unprocessed heartbeat of space-time, pulsing through the void. Imagine an entity that never speaks, never moves in the way we understand motion, and never signals its presence through ordinary means, yet profoundly influences its environment silently and profoundly. That is a black hole. But could such an entity be likened to an observer? Not in the traditional conscious sense, but through the behavior it displays in its interactions with the universe. When we peer deeply into black holes, we don't just confront cosmic silence, we confront the possibility that these dense gravitational pits might play roles that mimic observation and memory. This comparison doesn't arise from fanciful analogy, but from serious attempts in theoretical physics to understand the role of information, entropy, and fundamental limits in the behavior of black holes. The journey begins with what black holes are known to do. They encode information. Any matter or energy that crosses the event horizon, no matter how complex, simple, organic, or energetic, leaves behind a trace, not through a photograph or a logbook, but through the subtle imprint it creates on the horizon's surface. This is the starting point of one of the most counterintuitive, yet widely accepted ideas in theoretical physics, that black holes do not obliterate information, but instead store it, albeit in a manner not yet fully understood. The comparison to an observer arises here. In quantum mechanics, the role of the observer has always been enigmatic. Does a particle exist in a particular state before being observed, or is it the act of observation that solidifies its position, velocity, or spin? Now consider black holes not as active participants with eyes or thoughts, but as entities that change state depending on what falls into them. They respond, they shift. The horizon encodes. Over time, as Stephen Hawking predicted, they evaporate through Hawking radiation. That radiation, though once thought to be random, might actually carry subtle patterns, signatures of everything that ever fell inside. This possibility brings us eerily close to saying that black holes don't just store data, they act like cosmic registrars, recording without comprehension, observing without awareness. But how could a black hole possibly act like an observer if it doesn't process or interpret the information? That's the boundary where physics meets philosophy. An observer in the human sense is a conscious agent, aware, interpreting, sentient. A black hole doesn't meet those criteria. But in physics, an observer isn't always a mind. It can also mean a reference point, a node in space-time where measurements and interactions can be traced. In that sense, black holes are uniquely privileged. They mark irreversible changes. They mark boundaries. And most strikingly, they force quantum information to leave an imprint.
So, could black holes be minds? Likely not. Could they be mirrors? Very much so. Mirrors that reflect the deepest rules of the universe. They show us how entropy accumulates, how information survives, how irreversible change imprints itself on reality. In doing so, they also echo the behavior of observers, not in feeling or thought, but in function.
Part 6. Could the universe then be a mind? That remains an open question, one that treads a narrow line between metaphysics and science. But the more we study black holes, the more they seem to behave like cosmic punctuation marks, not just full stops in the stories of stars, but clauses that modify the sentence of reality itself. They are boundaries, yes, but also reflectors. They tell us where change becomes permanent, where information gets locked in, and where entropy speaks loudest. And in that role, as silent, speechless observers of the cosmos, black holes might be less like ghosts and more like lenses, not eyes that see but surfaces that encode, not minds that think but boundaries that remember. In a universe governed by information and shaped by gravity, that might be the closest thing we'll ever encounter to a mirror with a mind.
What happens to time inside a black hole? How does it differ from our everyday experiences? And could it even allow for phenomena like infinite thought during infall?
Black holes are the ultimate distorters of space-time. Time dilation, a phenomenon first predicted by Einstein's theory of relativity, becomes extreme in the presence of a black hole's immense gravity. The event horizon marks the boundary where this effect becomes especially pronounced. Time, as we understand it, froze consistently and predictably in the world we experience every day. Yet, in the realm of black holes, time becomes something malleable, twisted beyond recognition. The laws of physics, as we know them, break down at the event horizon of a black hole. As an object gets closer to the event horizon, time for that object slows down relative to an observer far away. In a very real sense, if you were to fall into a black hole, it might seem like time freezes for you as you approach the event horizon, while to an external observer you would appear to slow down and never quite reach the event horizon.
This extreme time dilation near black holes is a direct consequence of the curvature of space-time caused by their enormous gravitational pull. The closer you get to a black hole, the stronger the gravitational field becomes, warping time itself.
From an outside observer's point of view, someone falling into a black hole seems to freeze in place, suspended at the event horizon. But for the person falling in, time continues to pass normally for them, and they would experience an uninterrupted descent into the black hole's interior, except, of course, for the violent forces at play. However, the reality of what happens inside the black hole is still largely speculative. What happens to time once you cross the event horizon, since nothing, not even light, can escape a black hole? The entire inside of the black hole is hidden from view. Time, according to general relativity, continues to flow inward toward the singularity at the center. The mind's perception of time could expand into an infinite experience, where a single moment stretches out indefinitely. This concept is more than just theoretical. It's based on the assumption that time dilation could be pushed to its extreme, where even a brief moment of perceived time could encompass what feels like an eternity from the perspective of the observer inside the black hole. From the external observer's point of view, the object falling in never quite seems to reach the singularity, frozen as it is at the event horizon. But from the perspective of the infalling object, it is a different story. Inside a black hole, time itself becomes stretched in strange ways. This stretching of time could theoretically lead to infinite experiences or perceptions for someone falling into the black hole. From a physics standpoint, The idea is rooted in the extreme time dilation that occurs as one approaches the singularity. This stretched perception could create the illusion of timelessness, where the passage of time becomes so warped that the boundaries between moments become irrelevant. It's as if the mind could be trapped in a timeless bubble, existing outside the normal flow of time as we understand it.
Yet, there's a crucial caveat here. The singularity at the center of a black hole represents a point where the known laws of physics break down. We cannot describe what happens at this singularity with our current understanding of physics. And it is here that our concept of time may no longer apply in any meaningful way.
In this state, one could theoretically experience an infinite stretch of thought, almost as if the mind could exist in a boundless, eternal now. But how can we interpret this? Could a person truly experience infinite thought as they fall toward the singularity?
The mind's ability to experience infinite thought within a black hole is therefore more of a philosophical or speculative idea rather than something grounded in observable science.
In any case, the idea that time inside a black hole could stretch into infinity provides a fascinating backdrop for considering the nature of consciousness itself. If time were to behave so differently within a black hole, could the mind somehow take advantage of this strange bending of time to experience eternity or infinite thought?
In principle, yes, but only under certain extreme conditions that go beyond the limits of our current understanding of consciousness and the physical universe. There are those who argue that consciousness might in fact be a product of time dilation. If time could be warped to such an extent, then perhaps the mind, when exposed to such extreme conditions, might find ways to experience altered states of awareness. Of course, this is all speculative, and we have no way of directly observing what happens inside a black hole. The physical conditions near the event horizon, as well as the nature of the singularity, present a fundamental challenge to our understanding of time and consciousness. However, the possibility of time behaving differently inside a black hole is undeniable. Whether this creates a space for infinite thought remains one of the many unanswered questions that make black holes some of the most mysterious and awe-inspiring objects in the universe. Perhaps consciousness is not limited to a straightforward progression of moments, but could be a more fluid, flexible construct that adapts to the time-distorting environments of a black hole.
Whether this results in infinite thought, a stretched perception, or a mind trapped in an eternal moment is still unknown. But in exploring the role of time inside a black hole, we are also exploring the deepest reaches of what it means to experience existence itself, caught between the relentless pull of gravity and the unknown future that awaits us as we venture deeper into
Black holes, in this sense, are more than just objects in space. They are gateways to entirely new ways of thinking about time, consciousness, and the very nature of reality. In the end, time inside a black hole doesn't behave like time on it stretches, bends, and warps in ways we can hardly imagine. As we try to peer into the darkness of black holes, we are confronted with the idea that time may not be a constant, unyielding force, but something far more malleable and fluid. The extreme effects of time dilation suggest that the fabric of space-time is not just a passive stage on which events unfold, but a dynamic participant in the events themselves. Part 7.
Cosmos.
When we think of entropy, we typically imagine disorder or chaos, the inevitable trend toward increasing randomness in isolated systems. But could there be a deeper connection between entropy and consciousness,
Could the way black holes organize entropy be similar to how our brains process information?
Surprisingly, black holes, some of the most enigmatic objects in the universe, offer surprising parallels to the cognitive processes
Some
that
physicists
govern our
liken the
awareness.
event horizon to a hard drive, storing data not in silicon, but in space-time's curve.
Its state, it's not emotion, but it's transformation, input to output, governed by cosmic logic. This isn't random chaos, it's computation of a kind. Computation, after all, is information's dance. Computers shuffle bits through gates, their behavior shaped by how data flows. Black holes do something eerily similar. Their structure reflecting what they've consumed, they manage entropy, balancing order and disorder in ways that echo a system's internal logic. They don't think or learn, but they react, their horizons shifting with each encounter. This resemblance prompts a bold thought. If consciousness ties to complex information processing, could black holes harbor a flicker of awareness? Not as minds, but as patterns.
This isn't to say black holes ponder the stars. They lack the plasticity of brains or the warmth of life.
They're not alive, but they're not inert.
Yet their density, information packed to spacetime's limit, suggests a kind of ultimate complexity.
They're sculpted by their past, active in their present, reshaping galaxies with every ripple.
In IET's terms, their integration might hint at something structural, a shadow of awareness too alien to recognize.
It posits consciousness as fundamental, like mass or charge, woven into reality's fabric.
A philosophical idea, panpsychism, pushes this further.
If true, black holes sit on this continuum, not as thinkers, but as thresholds where information reaches extremes. A rock holds a trace, a brain holds a flood, and the difference is degree, not kind. Near event horizons, encoding reality's details, might embody awareness in its rawest form, not feeling, but being, a cosmic reflection of structure itself. They don't dream, yet they respond, transforming all they touch. This view reframes black holes. They're not traps, but engines, maximizing complexity as they warp space-time. Their collisions send waves that shape nearby reality, not passively, but actively.
Physicists sometimes call black holes cosmic memory banks, not for minds, but for information stored beyond our reach.
A hint that where patterns converge, something like consciousness might stir. This isn't sentience, it's potential. Their gravity echoes the past. Every star, every particle leaves a mark. This encoding isn't readable, but it's real, altering how black holes behave. If consciousness is tied to how systems hold and process complexity, black holes offer a mirror, not alive, but resonant with order hidden in collapse. Our minds evolve layer by layer, atoms weaving patterns until reflection emerged. They show what information can do when pushed to its limits. Perhaps we're asking the wrong question. Instead of our black holes conscious, we might ask, is consciousness broader than we think?
They're not intelligent, but they're formational, hinting that awareness might be less a spark than a spectrum written into physics itself.
Black holes don't mimic brains, but they reveal a truth. Complexity breeds possibility. If it happened once, why not elsewhere? It could flicker wherever information weaves tight enough, from neurons to event horizons. Consciousness born of complexity may not be confined to flesh. Black holes don't watch the cosmos.
but they reflect its deepest truths.
They remind us that meaning isn't absent in the dark, it's waiting, encoded in complexity, ready to reshape how we see ourselves, and that
The universe builds patterns, and in those patterns lies potential, not minds, but echoes. Black holes with their encoded histories stand as testaments to this idea, not as thinkers, but as possibilities.
Stars.
In the vastness of space, beyond stars and galaxies, lies a realm where reality unravels.
Part 3. Here, the laws of physics tremble, equations falter, and the universe itself seems to pause.
This is the singularity, a black hole's heart.
A forbidden zone where time twists, space collapses, and comprehension fails.
More than a mystery, it's a challenge to everything we know about existence.
From dying stars to quantum frontiers, this exploration dives into the singularity's enigma, asking, is it the end of physics or the gateway to a deeper truth? Now picture a star, massive and ancient, its fires fading as its core collapses. Atoms shatter, space compresses, and the star shrinks toward a point of no return. Gravity takes over, crushing matter into oblivion. Crossing the event horizon, it becomes a black hole. Here, density surges to infinity. Space-time curves beyond measure, and the rules governing the cosmos, motion, light, time, lose all meaning. But at its core lies something stranger, a singularity. General relativity, Einstein's masterpiece, predicts this collapse. But its equations scream infinity, a signal not of victory, but of defeat.
this isn't just a cosmic quirk. The singularity is a boundary where reality breaks.
Gravity, pressure, temperature, all soar to impossible extremes, defying the tools that chart galaxies and orbits. It's as if the universe, faced with its own limits, refuses to explain itself, leaving us with a tear in the fabric of existence. General relativity, which elegantly describes planetary paths and black hole edges, thrives on smooth, predictable space-time. This failure is profound. It guides spacecraft and predicts cosmic dances. But at the singularity, it crumbles. The curvature of space-time spikes, equations yield nonsense, and physics as we know it stops. Infinity isn't an answer, it's a confession that our understanding is incomplete. A sign that the singularity hides something our theories can't yet grasp. Roger Penrose and Stephen Hawking proved this isn't a fluke. This isn't speculation, it's woven into the universe's laws. When stars die or black holes form, gravity ensures a point where space-time fails. Their theorems show that singularities are inevitable in extreme collapse. The singularity isn't just a place, it's a question, daring us to find what lies beyond. A cosmic truth that demands we rethink reality itself. If relativity falters, where do we turn? The answer lies in uniting two titans: general relativity, master of the vast, and quantum mechanics, ruler of the small.
Relativity's smooth curves clash with quantum's chaotic probabilities.
These theories don't blend easily. This clash is no mere theory.
But their fusion, quantum gravity, offers hope.
At the singularity, where scales shrink to nothingness, quantum effects might tame the infinite, revealing a reality relativity can't see. At the singularity, these worlds collide, and neither alone can solve the puzzle. Relativity sees space-time as a fluid canvas, warped by mass. Quantum mechanics insists particles behave in waves, entangled across distances, governed by chance. One path forward is loop quantum gravity, a bold idea that reimagines space-time itself. Instead of a smooth fabric, it proposes a granular structure, tiny loops, like atoms of space, woven into reality.
Quantum gravity seeks a new language, one that might dissolve the singularity's chaos into something comprehensible.
These loops set a limit. Matter can't compress forever. The singularity in this view isn't a point but a barrier, a cosmic no further, where physics pivots. At the Planck scale, space-time resists, halting the collapse before infinity takes hold.
This changes everything.
If space-time is discrete, the infinite density of a singularity vanishes, replaced by a finite quantum state. The collapse might pause, even reverse, suggesting black holes aren't tombs, but stages for transformation,
where singularities mark beginnings, not ends. Loop quantum gravity doesn't just dodge infinity. It hints at a universe where chaos gives way to order.
Taking this further, physicist Carlo Rovelli proposes the Planck star.
From outside, the black hole seems frozen. At the Planck scale, unimaginably small, the collapse halts, forming a dense quantum core, a Planck star.
When the star collapses, quantum pressure fights back, countering gravity's crush. This isn't science fiction. Its event horizon veils what might reverse the collapse, turning the black hole into a white hole.
A gateway spewing light and matter, perhaps to another universe.
A Planck star bridges the black hole's birth and death, hinting that what seems lost might return, transformed in a cycle of cosmic renewal. String theory offers another vision, the fuzzball. It's a radical rethink of collapse, suggesting singularities are illusions masked by our limited view. Here, the singularity isn't a point, but a tangled web of vibrating strings, fundamental threads of reality. These strings, packed with quantum energy, form a complex fuzzy structure, not a featureless void.
From afar, the fuzzball looks like a black hole, its event horizon smooth. But inside, it hums with activity, a chaotic dance of strings, encoding everything the black hole consumed.
The singularity dissolves, replaced by a quantum knot, too intricate to call infinite. Fuzzballs challenge our assumptions.
They suggest black holes aren't simple, but wildly complex, their interiors alive with possibilities.
The singularity in this light is a misnomer, a region not of destruction, but a vibrant, microscopic structure, holding secrets in its quantum weave.
These ideas, loop quantum gravity, Planck stars, fuzzballs, reframe the singularity.
It's not a cosmic dead end, but a frontier.
Where physics once saw ruin, we now glimpse potential. A bounce, a rebirth, a web of strings. Black holes, far from devouring reality, might connect it, linking past to future, one universe to another.
The shift echoes broader questions.
The singularity isn't chaos, it's a puzzle, demanding we look deeper,
beyond the limits of our current laws. The forbidden zone might not forbid understanding, it might invite it.
If singularities mark transitions, not endings, what does that mean for reality's fabric?
Could they, like information or consciousness, hint at a universe more ordered than we dared imagine?
Urging us to rethink time, space, and existence itself.
Yet, for all these theories, the singularity remains elusive. We can't peer inside, can't test the Planck star's pulse, or touch a fuzzball's strings. It's a boundary not just of physics, but of knowing.
But boundaries aren't endings. They're challenges. A place where our tools, our math, our minds hit a wall.
Every limit in science, from gravity's pull to light speed, has pushed us to see more, not less.
The singularity beckons because it defies. It forces us to confront infinity, to question certainty, to seek a truth beyond the chaos. We don't know yet, but the search, driven by minds like Penrose, Hawking, and Ravelli, is its own revelation. Is it a void? A portal? A mirror of reality's deepest code?
Part 4. In their mystery lies a call to explore, to imagine, to reach for a universe where even the forbidden yields meaning.
A reminder that the universe rewards those who dare to ask.
It's known as the cosmic censorship conjecture, and it suggests that nature, in all her complexity, has a sense of modesty.
There's an unspoken rule in the universe, one that may not be written into the laws of physics, but is whispered within the equations. Even when she creates something as violent and unimaginable as a singularity, a region of infinite density and unfathomable force, she keeps it hidden, concealed, veiled behind the black curtain of an event horizon. This is the realm of the naked singularity, and it could be the universe's most shocking form of honesty.
But what if she doesn't?
What if there are moments when that curtain slips, when the veil lifts, and the singularity is exposed for all to see?